Today, we're diving into the crucial topic of database integration, a fundamental aspect of modern application development. This involves seamlessly connecting various applications to both structured and unstructured data sources, which is essential. Let's begin by exploring the core concepts of relational databases, which are foundational for many systems. These are the essential building blocks that enable efficient and organized management of structured data. First, we have tables, the primary structures for organizing information in a relational database. Tables are organized collections of rows and columns, designed to store specific types of data. Within tables, rows and columns serve distinct, yet interconnected purposes. Rows represent individual records, while columns define the specific attributes or fields of that data. A primary key is an absolutely vital component in every relational table. It's a unique identifier for each row, ensuring data uniqueness and integrity within a table. Then we have the foreign key, which plays a crucial role in establishing connections. A foreign key establishes relationships between tables by referencing a primary key in another table. Finally, schemas define the overall blueprint or structure of our entire database. They define table names, data types for columns, and various constraints that govern the data. Now, let's delve into the key features that make relational databases so robust and reliable. These features are critical for ensuring data reliability, consistency, and a well-defined, predictable structure. First, we have the crucial ACID properties, which are fundamental for transaction integrity and reliability. Atomicity ensures transactions are all or nothing, meaning they either fully complete or don't happen at all. Consistency means data always remains valid and follows predefined rules before and after transactions. Next, let's discuss SQL interaction, the standard language for working with relational databases. Structured Query Language, or SQL, is used for efficient data definition and powerful manipulation capabilities. Commands like SELECT, INSERT, UPDATE, and DELETE are fundamental to effective data management and interaction. Data integrity is another vital feature, ensuring the accuracy and reliability of our information. It ensures accuracy and reliability through constraints like NOTNULL and UNIQUE, maintaining data quality. This prevents invalid data from being entered, thereby significantly enhancing overall data quality. Finally, relational databases excel at defining and managing complex data relationships efficiently. They support one-to-one, one-to-many, and many-to-many associations between various tables. These relationships optimize data organization, reduce redundancy, and improve retrieval efficiency. Now, let's shift our focus to understanding NoSQL databases, a different paradigm for data management. NoSQL databases offer powerful alternatives, moving beyond traditional relational models for modern data needs. One key characteristic of NoSQL is its flexible, schemaless design, which offers great adaptability. Data can be stored without a predefined schema, offering high flexibility for evolving data structures. Another significant advantage is NoSQL's inherent horizontal scalability, crucial for growth. It scales out by adding more servers, ideal for managing large data volumes and heavy user loads. NoSQL databases are also characterized by their distributed architecture, built for resilience. They are designed to operate across multiple nodes, enhancing both resilience and overall performance significantly. Let's look at specific types, starting with document databases, a popular NoSQL category. These store data as flexible, JSON-like documents. Examples include MongoDB and COUCHDB. Another common type is key-value stores, known for their simplicity and speed. They use simple key-value pairs for extremely fast data retrieval, like Redis and DynaMongoDB. Let's explore the typical workflow of CRUD operations, understanding how data interacts with applications and databases. It all begins with user interaction, where a user decides to create, read, update, or delete data. This interaction then triggers the client to send an appropriate HTTP request to the server, initiating the process. Next, the server receives and processes this request, determining what database action needs to be performed. The server then executes the corresponding CRUD operation directly on the database, manipulating the data. Finally, the database's response is sent back through the server to the client, completing the workflow. Now, let's dive into setting up MySQL and performing some basic interactions with this popular relational database. We'll specifically focus on getting started with MySQL, a powerful relational database within a Linux environment. First, you'll need to update your local package index to ensure you get the latest software information. You can do this by running the command sudo apt update in your terminal, which refreshes the package list. Next, we'll proceed to install both the MySQL server and the client tools necessary for interaction. Use sudo apt install MySQL server to install the complete MySQL package, including the server and client components. Once installed, you can access the MySQL command line interface to start interacting with your database. To log in, type MySQL uroot, then enter your root password when prompted, gaining access to the shell. Let's create a new database, which will be named ExampleDB, to store our data. You can achieve this by executing the simple SQL command created exampledb in the MySQL shell. Moving on, let's explore the basic CRUD operations in MongoDB, a popular NoSQL document database. We will learn how to interact with document-oriented data efficiently using the Mongo shell, its command line interface. First, let's see how to insert a new document, which is essentially creating a new record in our database. The DB collection insertone method allows you to add a single new document into a specified collection, creating new records. This code snippet demonstrates inserting a user document with name, email, and age into the user's collection. Next, we'll explore how to find and retrieve documents from our collection, effectively reading our data. The DB collection find method is used to retrieve documents, either all of them or those matching specific criteria. Here, we use DB users find to retrieve all user documents where the age is greater than 25. Now, let's learn how to update an existing document, modifying its data within the collection. The DB collection updateone method modifies a single document based on a filter, often using the set operator. This code updates the document for John Doe, changing their age to 31 using the set operator. Finally, we'll cover how to delete a document, removing unwanted data from our collection. The DB collection deleteone method efficiently removes a single document that perfectly matches your specified filter. This command will delete the document where the name field is John Doe from the user's collection. Let's outline the key steps involved in effective database design, from initial ideas to final implementation. We'll trace the journey from understanding your application's requirements all the way to its physical implementation. Requirement analysis involves identifying application needs, defining entities, their attributes, and relationships between them. Conceptual design focuses on creating an entity relationship, or ER diagram, to visualize data entities and their associations. Logical design maps the ER diagram into tables, defining primary and foreign keys, and normalizing data for efficiency. Physical design involves implementing the database schema using a DBMS, choosing appropriate data types and storage options. All right, let's wrap up our discussion with a concise summary of the key points we've covered in our database integration journey. We'll now highlight the most important takeaways you should remember about effective database integration in your projects. Relational databases like MySQL and PostgreSQL use structured tables, primary/foreign keys, and SQL for efficient data management. NoSQL databases, such as MongoDB, offer flexible, schemaless document storage, ideal for scalable and diverse data requirements. CRUD operations, meaning create, read, update, and delete, are fundamental for interacting with data in all web applications. Effective database design involves requirement analysis, conceptual, logical, and physical design, including normalization techniques. Connecting databases to web applications requires drivers, secure credentials, connection pooling, and thorough error handling for reliability.